Okay, Assalamualaikum dan salam sejahtera.
Waalaikumsalam, Doktor.
Okay, for these notes, I think I could make it a little bit faster. So I think I also upload these notes. So this is just a basic calculation about the drag force and the lift force. So we have two notes here. So for example, example 1 here. So a rectangular wing on a small airplane has 1.3 meter chord and 10 meter span when flying in air at 220 km per hour. The wing experiences a total aerodynamic force of 18 kilonewton here. If the lift to drag ratio is 3, determine the lift coefficient of the wing. So because it say the total aerodynamic force, so means this is the idea. So, and then we know that the lift to drag ratio is 3, so we could have this one. So, and then we could calculate the percentage, the drag force and also the lift force. And then we could calculate the lift coefficient by using this equation. So you get it is equal to 0.587. So, and then this is example 2. In a lift and drag experiment performed in a wind tunnel, a NACA 0012 was used. The aerofoil has a 15 centimeter chord and span length of 45 centimeters. Using a force measuring device, a lift force of 60 Newton was measured on the airfoil for a Reynolds number 4.586 times 10 to the power of 5. The lift coefficient for this airfoil is given by CL 2 pi sine alpha. So this is actually for the common aerofoil, where alpha is the angle of attack under the given condition. So what is the angle of attack in degrees? So means that you have the force here. So I want to explain a little bit about the force measuring device. So normally, if you want to conduct experiment in by using aerofoil to check the lift force, drag force, and so on, you may use wind tunnel. So in UTM, we have wind tunnel. So at the same time, you could use water tunnel. In fluid mechanics, we have a water tunnel. Okay, this is actually the same things. The wind tunnel, you will use air as the medium, as the moving fluid. But in water tunnel, you are using water instead of air as a moving fluid. So the idea, actually the another element that you need to understand here is it's going back about the similarity. So mean, for example, if you want to test about aerofoil, so it will be used for a large aeroplane, Boeing, for example, Cessna. Okay, the wing is actually big, relatively big compared to what we have, what our facility has. So in Europe, they may have very large wind tunnel. As I know, last time I found it somewhere, the largest wind tunnel is actually as big as a stadium, I think. They could test a real helicopter inside that wind tunnel. Okay, so if you could see the car maker, Audi, BMW, they could put their actual car in their wind tunnel. So they have a very big wind tunnel. But in UTM, yes, we have wind tunnel. So our wind tunnel is actually the largest wind tunnel in Southeast Asia. Not in Asia, because Japan and Korea, they have the bigger wind tunnel for their automotive industry. Okay, but the problem when you do wind tunnel in small scale, in a intermediate scale of wind tunnel, the size is very important. You need to reduce your size, but because you are using wind, you are using air, the density of air is very small. So means the effect is, the problem is, if you scaling down your object, become smaller and smaller, at certain ratio, the boundary layer thickness will not decrease. Okay, that's why you need to actually the relation between the boundary layer thickness and the experimental way of this one is the boundary layer thickness will not decrease. So means that the boundary layer thickness will at certain ratio, start at certain ratio. So the boundary layer thickness is not increased. It's not decreased. So you should understand. So you have a big model. So maybe you will have a boundary layer here. So when you scale it down, so maybe the boundary layer will reduce a little bit. So means that the ratio from this boundary layer and this boundary layer can be acceptable. Compare with the size of the object. But if you using a small object, so the boundary layer here, okay, will give you a same like this one. Whether you means if you are using different size of object, but the boundary layer will remain the same. So that's the effect of boundary layer. Okay. So and then at this moment, okay, at this time, okay, actually you cannot conduct your experiment by using the wind tunnel. So the rule of thumb on scaling down your object in wind tunnel is maximum is around 1/4 or 1/3. Might be you could reduce to 1 to 3 or 1 to 4. In UTM wind tunnel, we have model of protons car. So the ratio model is 1 to 4. Mean it's scaled down 25% maximum. If not, the calculation or the assumption, the value that we get from that wind tunnel is actually not reflect the real one. Okay. So at the same time, the problems about the wind tunnel is you need to have a very, very smooth surface, because if the surface is rough, so the boundary layer will change. So and then it will not reflect the real boundary layer that occur in full size. Okay, to overcome this problem, you may use water tunnel, because water tunnel can be conducted by using a small object, because density of water is extremely high compared to wind. So it is 1,000 kilogram per meter cube compared to air, which is 1.23 kilogram per meter cube. The viscosity of water is quite high, so means that the boundary layer effect is actually the decrement or the formation of boundary layer on water tunnel is actually following the ratio, because the density, the viscosity of water is quite high. It can give influence in the way. Okay, but however, for water tunnel, its disadvantage is you cannot give high speed. That's why you need to learn about the similarity to reduce the object. At the same time, you must make sure that the velocity of water is actually reflecting the real velocity. Okay, that's what it means if you want to do your master project later on. So we have this one, and then you are welcome to fluid mechanics for doing your master project later on. Okay, so and then the wind tunnel there, so they will have 3-axis load sensor, and that load sensor will measure everything: the lift force, the drag force, and also the moment. Okay. So and then for example, so this is the Renault number. So okay, so it is given that Renault number is 4.5. So we compare with the equation here. So we could get that the velocity is 45 meter per second. So we are using this equation. So and then we equalize with the equation for the lift coefficient given in the question. So this is actually the common aerofoil, the normal aerofoil sinusoidal curve actually. So we found that the angle of attack alpha is 6.52 degree. So and then for example 3, an aircraft with a mass including payload 1,000 kilogram. So payload here is actually the mass of aeroplane aircraft plus load that are carried by the aircraft. It's designed to cruise at speed 80 meters per second at a height of 10 kilometers. The effective wing area approximately 15 meters square. Determine the lift coefficient and the angle of attack. What power is required by the airfoil during cruise? Assume a conventional aerofoil. So what I want to show in this question is sometimes we need to calculate power. So first, lift coefficient. So this is the lift coefficient. So and then this is just a reminder for you. So if you are doing calculating aircraft and so on, so please make sure that you pay attention to the height, because when the height increase, so the density of air will reduce. So that's why here the row here, so we are using the value for 10 kilometers. You may have, if you have textbooks, you may have at the back there are table to show the value of density of air, standard atmospheric air, according to the height. So it is might be have around 18,000 meters, I think. Okay, so means that at around 10 kilometers, so the density is reduced into 0.412. So you need to use this value, then you get the lift coefficient. You substitute with the equation and you get the alpha 4.53. And then the power, to calculate the power is drag force times the velocity. So the drag force here is 0.0065. So I think this is taken from the graph. So let's say the 4.53. So I think it's taken from 4.53. So around this one, I think. So and then Naka here. So I think, I'm not so sure. Okay. So because this is a very simple question, so I just want to explain you, at least you know which how to conduct the calculation about lift force and drag force. Okay, for example, for a 1500 kilogram aircraft is designed to carry payload 3000 Newton when cruising at 80 meter per second at a height 10 kilometer. The effective wing area is 20 meters square. Assuming a conventional airfoil, calculate the takeoff speed if an angle of attack is 10 degrees, the stall speed when landing, and the power required at cruise if 45% of the power is needed to move the airfoil. So the takeoff speed, so means that the lift force is equal 1.22. So okay, so let's say this is the value that we need. So this is the equation, and then we substitute. So what I want to show you here is the value here, 3000, you must add with the aircraft, because this is the total mass for that aircraft, and we could get the value of velocity here. And then the stall speed, oh, I think this is come from this from the graph. Okay, so we have the stall CL here is 1.72. Okay, so and then we substitute in this equation, so we get the velocity is 50 meter per second. So and then to calculate the power, so this is the equation of power. And then here, because we have 45% power will be used to move the airfoil, so means we need to have an extra 45%. So we know that it is actually shows the efficiency actually. So okay, so and then we could have 13,700 over 0.45. So we need required for 30,400 watt. This is a few. Okay. Then this is the last question, the simple one. Propose aircraft to resemble a huge airfoil. Flying it as shown below, a wingspan will be 200 meters. So quite a long one. So I'm not sure this is the original design or not. So the chord is 30 meters. So assuming a conventional airfoil, the total mass of the aircraft, including payload, for a design speed of 800 km per hour at elevation of 8 km, and also calculate the power requirement. So let's say the conventional aerofoil, so we take the value of CL over CD, 47.6 at CL 0.3. So we substitute the value of CL here, 0.3, then we could get the mass is 2.38 times 10 by the power of 6 kilogram. So, and then we substitute, we could calculate the power here, FD time V. So it is around 490,000 watt or 657 horsepower. So means that the power required for the aircraft is 657 horsepower. Okay, this is for means very general calculation for problems about the lift force and the drag force. Okay, now we go for a detailed one, okay, regarding to the boundary layer. So for example, in this question 1, a timber is pulled by a boat during the river with force of 200 Newton, as shown in figure 1. Only half of the timber above the water. So half is actually submerged in water like this. Determine the drag force due to the front surface. So in this situation, you need to know that one object here, we have a timber. So, and then the water is, the area that submerged is half of the timber. And then you could imagine that at the front surface here, okay, the water will hit perpendicular. So means it will give us a drag force due to the surface. Okay, and then the boundary layer occur at this surface, the surface which is parallel to the flow motion. Okay, so mean at this surface, the boundary layer will occur. So, and then it will give us shear stress. At the same time, we could calculate means we have boundary layer, so we could calculate drag force. So mean the drag force comes from the boundary layer, and also the drag force come from this front surface. Okay, that's the first thing. And the second one is, if you see the picture, you could see that the boat moving at 2 meters per second, but the river is also moved at 1 meter per second. So previously in our theoretical class, about boundary layer, we always assume that the plate here is 0 meter per second. It's fixed. It's not moving. Only the free stream velocity here is coming at certain velocity. But in this situation, we found that both is moving. Our object is moving at certain velocity, and the fluid is also moving at certain velocity. So in this situation, as an engineer, I think you should to reconstruct your free body diagram. Okay, so means that you use the idea of relative velocity. You must make sure that you will have this one. You have situation where your object is fixed, not moving, and you will have the free stream velocity at certain speed. So what you need to do is you use the idea of relative velocity. So if the velocity here is moving in reverse direction, not in the same direction, so you need to add the velocity. So mean you could have the timber is fixed, but the water flowing to the timber is 3 meters per second. So mean that you need to calculate with all the boundary layer equation by using the velocity 3 meters per second. So, and then because we don't know whether it is laminar or turbulent, so and then we don't know about the velocity profile, so it is okay for us to use Blasius, all the Blasius assumption, all the Blasius equation, if the laminar boundary layer is laminar, if the boundary layer is laminar, and we could use 1/7 power law if the boundary layer is turbulent. Okay, so okay, so so we skip all the calculation. So because this question is the applied question, so you may comes with the equation. So let's say the CD for laminar, this one you may take from the Blasius solution, and this is the CD, the drag force. Bear in mind that there are two CD. One is a local drag coefficient, one is a total drag coefficient. Sometimes they just use drag coefficient without word total. Okay. Okay, so we take the capital D, so the drag coefficient for laminar is here and turbulent is here. So what we need to do, we need to check whether the Reynolds number is turbulent or not. So we check rho ux over mu, and again, please make sure that the velocity here is actually the relative velocity. So we use 2 plus 1. So and then we calculate, we found it is equal to 3 times 10 by the power of 7. So we assume it is fully turbulent now. So and then we learned previously the effect of laminar boundary layer. So we need to check, okay, because okay, let's say we get the common value. We assume that 5 times 10 by the power of 5 is the transition. So we equalize with rho ux over mu. We substitute everything. So we found that the length of laminar boundary layer means the x here is 0.17 meters. So if we compare 0.17 meters with the total length of the timber, which is 10 meter, so we found that the 1.75 meter is less than 10%. It's very, very small. It's only 17 centimeters compared with 10 meters. So maybe we could say that the existence of laminar boundary layer can be ignored, okay, because it is too small. Okay. Now we need to calculate the drag force using the equation of turbulent boundary layer. So we know the CD, and we need to determine what is the A. So A is the section, the A is the area, and you must understand that area is actually, so we have a timber here, and water is half of this. And the area is actually the area of this one, the area that give shear stress, not the front area. The front area here is not counted. Please bear in mind, because certain students, they take only front area because the question asks to find the drag force for the front area. So that's not the proper solution. So you need to be careful. Please make sure that you use parameter that related to the equation. Okay, so here, because I use the idea of boundary layer, so mean we need to calculate the area that influenced by the boundary layer. So mean the influence, the area of this one. That's why we calculate it as 1 over 2, half of the parameter 2 pi r, and we times with L, the length of this timber, and we get it is around 6.2 meters square. Okay, please, when you answer final question, final exam and also test, please use until 3 or 4 decimal. Okay, showing that you are very precise in calculation. I'm going to say the short one. Okay, so for example, it is just 6.2 meters square here. So we substitute into this equation. So we use the CD for the 1/7 power law because it is turbulent, and then we get the total. The force here, the drag force here is 56.1. So then, okay, as an engineer, you should understand that the question is asking about the front surface, the drag about the front surface here, and then you may have certain ideas. You could make a conclusion that the 200 newtons, okay, applied by the boat is actually to overcome resistance that come from the front surface here, and also resistance that comes from the boundary layer. So means that the force at site mean force due to the boundary layer plus the force at front surface here will give us 200. So if the force from the boundary layer is 65.1, so you will have X here. The force due to the front surface is 134.9 Newton. Okay, any question?
Yes, doctor.
Okay.
I have two questions if you don't mind.
Okay.
The first one, we use Reynolds number for turbulent boundary layer.
Yes.
Why you return to the Reynolds of laminar boundary layer to calculate X?
This one?
Yes, doctor.
Okay.
We use Reynolds number for turbulent.
Okay. So
Why you use again Reynolds number for laminar? to
Okay.
calculate X.
Okay.
The second question, please.
Wait. I
I'm
will answer
sorry. I'm
that
sorry.
first. Okay. One
Sorry,
by one.
doctor.
Okay. Don't give me
Okay.
all the question. I will not
Okay,
remember
doctor.
it.
I'm
Okay.
sorry. I'm sorry.
Okay. So we have a timber here. Okay. So in this stage, we calculate the Reynolds number here is the Reynolds number at the end of this timber. Okay, so we get it is 3 times 10 by the power of 7. So it is totally turbulent. Okay, but okay, previously in chapter 6, I teach you how to solve problem if lamina need to be accounted in the calculation. Do you remember it yesterday?
Actually, no, doctor.
You are
To
not
be
coming or
honest,
you not remember?
no. Because I didn't study
Okay,
the
so
lecture of yesterday.
just look back
I'm
your
sorry.
notes. Okay, yesterday notes. So I give you uh, notes about how to calculate boundary layer thickness, drag, and so on and so forth. If lamina boundary layer is actually cannot be ignored. Might be the existence of lamina boundary layer is 40%, 30%, or more than that. Okay, so because we have that, okay, because we have that idea, mean to make sure that our calculation is precise. That's why we need to calculate the lamina boundary layer here, because we want to know whether lamina boundary layer is only a small portion here, or lamina boundary layer is actually maybe 70% before the turbulent boundary layer occur. Okay, how to calculate this one? Okay, we know that lamina boundary layer occur until Reynolds transition, which is 5 times 10 to the power of 5. So after this, lamina boundary layer will 100% change to turbulent. Okay, that's why we use 5 times 10 to the power of 5. We equalize with rho ux over mu. Then we could calculate the x here. So the x here will represent how long lamina boundary layer will occur. The length of lamina boundary layer. So according to this calculation, so we get 0.17. So means now you should make a justification. You should justify your result. So mean the length of lamina boundary layer is just 0.17 meter. So according to this question, so we have 10 meters. So mean 0.17 meter is relatively very small compared with 10 meters. Then we
Yes.
could say that lamina boundary layer can be ignored. So if lamina boundary layer cannot be ignored, so mean you need to use the idea. You need to use idea to merge the lamina and turbulent boundary layer. Okay, can you get it?
Yes, doctor.
Okay, so second question.
If please, if we have the similar case, but the object move not the same direction with the fluid.
Yes,
I am asking about velocity,
yes. Why
relative
it,
velocity.
yes, why it become two? And why
Yes,
it become three?
no, doctor. In this case, the object move in opposite direction of the fluid.
Yes.
I'm asking if the object move in the same direction. The relative velocity also we add
Okay. No, 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 no.
or subtract.
No. So you need to deduct if the vote is 2 meter per second at this direction, and uh, the river is flowing at the same direction here, but with 1 meter per second, let's say.
Yes.
So the relative velocity is equal to 1 meter per second.
This is my question.
Okay. So
Thank
please
you,
make
doctor.
sure this one.
Yes, thank you,
Okay.
doctor.
Okay. So I think you should understand this one. Sometimes the application of boundary layer is not just the final answer. Okay, it might be you need to add the mechanical ideas, the mechanical engineering that you learned previously to solve the problems. Because the calculation of boundary layer is actually to give you a drag force, as it's I could say in general the last product of boundary layer is the lift and the drag force, as I said in the previous in the first lecture for chapter 4, I think. So we are talking about lift force, drag force, and so on. Okay, so and then I give you a similar question like this one. For example, we have a flat plate 3 times 1.5 meter here, hail in water moving 5 meter per second, parallel to its length, determine the power required to overcome the drag. So this is, again, we ask about the power. So this is the value of mu and rho. So we have the u here. So this is the length 3 meters. So this is the length of 1.5 meter, the width. Okay, so we check the Reynolds numbers. So it is 1.5 times 10 to the power of 7. So it is turbulent. So and then again we check the Reynolds critical. So Reynolds critical or Reynolds transition. So we found that the value of x is 0.1 meter, the laminar boundary layer. So means that 0.1 compared to 3 meters, it's quite small. So we ignore the boundary layer. So and then because it is turbulent, so we write the value of CD for turbulent boundary layer here. So it is equal to these numbers, 0.00271. So this is the drag force. We calculate into this one. We know the value of A. So it is 1.5 times 3. So we get 152.4 Newton. But you must remember, if we have plate like this, so the top surface will give you drag force as well as the bottom surface. So means that you need to multiply with 2. So and then you get 304.8 newtons. So and then to calculate the power, you will have drag times velocity. So it is around 1524 watt. Okay, so this is the okay, so we start this one. Okay, so let's say for question number 3, we have water at 20 degrees Celsius, 1 atm, flows at 2 meter per second, past a smooth flat plate, 1 meter long and 60 meter wide. What is the trailing edge boundary layer thickness? What is the trailing edge wall shear stress? And what is the drag force on one side of the plate? So and then this is the data. So we calculate the Reynolds number. So we find that it is 2 times 10 by the power of 6. So it is turbulent. So we check the Reynolds number, the transition Reynolds number, we check the length of the laminar boundary layer. So it is 0.25. So if we compare 0.25 with 1 meter long, so it is 25%. So mean 25% is actually a large portion, mean 1/4 of the total plate is actually laminar. So we need to consider the laminar boundary layer. So to make it simple, so we will use Blasius solution for laminar, and we will use turbulent 17 power law for the turbulent. Blasius solution for the laminar and 17 power law for the turbulent. Okay, so this idea is, it starts I already explained it yesterday. So we have a laminar boundary layer here, and then it's changed into turbulent. So and then at this point we found that the shear item, the shear value here is the delta. So first we calculate the delta from the laminar boundary layer. So okay, why we calculate it by using the laminar first? Because we know the location of this Reynolds number. So this is because at this point, okay, because at this point the Reynolds number is 5 times 10 by the power of 5. Okay, so we take the The Reynolds critical here is 5 times 10 by the power of 5. So we substitute it here, so we get it is 1.768 times 10 to the power of minus 3. So and then, okay, we could substitute the value of delta here to the equation of the delta for turbulent. Okay, because this value, this point actually shared by the laminar and also the turbulent boundary layer. So if we substitute the value of delta using the equation for the delta for turbulent, so the unknown is the value of x1 here, and we could get x1 here is equal to 0.066 meter. So what is x1? So x1 is actually the distance from here to the imaginary starting point of turbulent boundary layer. Okay, this is x1. So and then why we need to calculate x1 here, because we need to know what is the total length from here to end of this plate. Because if we want to use turbulent boundary layer, we need to make sure the length is start from the origin. So this is actually the imaginary starting point, the imaginary origin for the turbulent boundary layer in this case. Okay, so we could calculate it as 1 minus 0.25. So because the total length is, the total length here is 1 meter. So we deduct with the length of laminar boundary layer 0.25, and then we add with this length, so which is 0.066. So we have the total length of turbulent boundary layer only is 0.816 meter. So and then we could calculate the Reynolds number for turbulent boundary layer only by substituting the L here equal to 0.816. So it is 1.6 times 10 to the power of 6. So and then we could calculate the boundary layer here, the boundary layer at the trailing edge at the end of the plate is by using the turbulent boundary layer. So this is the equation delta, and we get, but make sure that you are using the Reynolds number from the turbulent. Okay, because we are using only the turbulent boundary layer. So we get it is equal to 0.0174 meters. So and then we could also calculate the shear stress at trailing edge. So and then it is by using the equation for the turbulent. So it is equal to 6.6 Newton per meter square. Okay, so and then, okay. So for drag force, okay, drag force is something else. Why? Because we have a laminar here, and then it start to a turbulent here, and we calculate the imaginary starting point of turbulent at this point. Okay. However, okay. Previously, we calculate the total or the final drag for the final boundary layer thickness at the end here by using the turbulent. So this is all turbulent boundary layer, and it is okay because we are taking this length for in our calculation. Okay, so it is okay for our previous calculation, but for the drag force, we cannot use the drag force, the CD, from the turbulent only. For the turbulent only, so we cannot use that. Because if we calculate the drag force only by using the CD of turbulent, of this one, we only calculating the drag force for this area only. We're not calculating area drag force influenced by the laminar boundary layer here. So it means that our calculation is totally wrong. But if we calculate drag force only use turbulent boundary layer, so means that we are adding unnecessary part here. Means this part is actually not exist, but we keep adding in our calculation. That means that that's also wrong. So what we do is we need to refer to table that I gave you in yesterday's lecture. So we need to comes out with equation of CD depends on the Reynolds critical. So let's say in this question, the Reynolds critical is 5 times 10 to the power of 5. So our CD here, K can be written as this one. So this is actually the 0.073 is actually the CD for the turbulent. So this is the CD of the idea is we calculate the drag force with 100% turbulent first, and then we need to deduct with certain parameter here to reflect or to reduce the unnecessary part here, because we are only take care about the laminar here. Okay, so but this number is actually comes with this with the curve fitting. So people doing the experiment start to plot a few things and then give some prediction of the value. Okay, so from this table, last time I give you table. So in Reynolds critical 5 times 10 to the power of 5. So this is the CD. So we use the CD, we calculate, so it is about 0.00316. So we substitute into this equation, so we could calculate the drag force here is equal 3.792 newtons. Okay, so this is the idea how to calculate when you have both laminar and turbulent. Okay, so we go for question 4. So in figure 1, shows a uniform flow past a flat plate. Determine the wall shear stress tau wall here between AD. So the question is determine the wall shear stress between AD, between the shear stress between this point to this point only. Okay, so this is actually the formation of the boundary layer. Okay, so and then assume that the profile is laminar and U here is Y over delta by the power of 1 over 2. So 1 over 2 is quite small. Maybe we could assume it is a laminar, it less than 1. So and then, so it is given that delta AB mean a boundary layer from A to B here is 0.5. And delta at CD, boundary layer at this CD is 0.16. So, and then it's given the density of air and also the dynamic viscosity for air. Okay, so this is all the data from the question. Okay, so we know that tau can be calculated by using the idea of rho u square d theta dx. Okay, and then we know that the u over u here is given as y over delta to the power of 1 over 2. Okay, so means what we need to do first, we need to calculate the value of theta here because we have theta here. So theta can be calculated by using our previous equation, 0 to delta u over u, 1 minus u over u dy. So you substitute here, and finally you will get it is equal to 1 over 6 delta. So you substitute it here, 1 over 6, and d here will become d delta. Okay, and now we could solve this problem. However, we cannot solve it by using a mathematical approach because the data is not well provided. Okay, the data is actually provided in terms of figure, so we need to use amount or anything from the figure. Okay, so first we need to understand is what is the meaning of d delta. So d delta here is actually the delta of the delta, mean the difference of the delta. So according to this diagram, it is found that we have 2 points, this point and this point, and each point here has their own delta. So this is 0.15 and this is 0.16. So mean the d delta means the difference between these two boundary layer thickness. So we deduct delta CD minus delta AB. So we get d delta is 0.01. So this is the value of d delta, and dx here means the difference of these 2 points. So it is given as 0.5. So we substitute dx as 0.5. Okay, then we know the value of u, we know the value of rho, and then we could calculate the tau is equal 1.007 times 10 to the power of -3. So this is the idea to solve problem of boundary layer. Okay,